afternoon. So, yeah, this semester's turned into a really busy one. I wasn't expecting it, but something's popped up that's it's taking a lot of my time. But I will try to have your exams graded and back to you sometime this week. So if not Wednesday, Friday's class for sure. But I haven't been able to do that yet. Anyway, today we'll keep moving on to the next section, 3.4, and this is titled "The Place of Parallels." And we're actually going to sort of we're going to sort of stray away from thinking about hyperbolic things for a second, and do something that we really need to do. Something you've been thinking about in one of your last homeworks. I think it was homework 3. Coming back to the alternate interior angle theorem, the converse of that. We still need to prove very important results, like the fact that Euclid's fifth postulate is equivalent to Playfair's postulate. So that's going to make it most of the section, and yeah. In fact, for homework 3 for that particular question, if you had read ahead in the textbook, if you had read the section, it answers pretty much all those questions. But this is something we need to prove. So the alternate interior angle theorem. What does it say? So it says if two lines are intersected by a third by a transversal, in such a way as to create two alternate interior angles that are congruent to each other, then the two lines are parallel. So by a transversal such that a pair of alternate interior angles formed is congruent Is it singular because I'm talking about a pair, or is it R because I'm talking about plural angles? It's not an English class, but
Nope.
I don't know. Formed, the pair is congruent, or the angles are, I don't know. Formed is congruent, then the lines are parallel. So one of your homework problems dealt with this quite significantly, and the converse of this statement. This statement is true in neutral geometry, so it's true. It's true in Euclidean and hyperbolic geometry. And the first thing I want to do is prove this. So let's prove it. And it turns out it's really just a result of the fact that neutral geometry is an incidence geometry. So we really just need the incidence facts. Let's see. So suppose we'll assume our hypotheses. So we've got two lines. Suppose L and M. Suppose L and M are two lines intersected by a transversal. At two distinct points. Two distinct points, we'll call them P and Q, respectively. All right, so do I want to give the transversal a name? No. Okay, so I've got two lines. Let's call them L and M. L and M. I have a transversal cutting through them, and it cuts through at 2 points. We'll call these points P and Q. By the way, why can I say cut through at 2 distinct points? Well, the only other option, if it doesn't cut through at 2 distinct points, is something like this, right, where they all sort of go through the same point. But in that case, there would be no way that I could satisfy these hypotheses that I have a pair of alternate congruent, or alternate interior angles that are congruent. So I suppose the very fact that I have this pair means that yes, I can assume they cut through it at 2 distinct points. So to save some writing, I'm going to rely on this picture. I don't really like doing this in proofs, but if you're going to start naming things without sort of explicitly writing down what they are, at least draw a picture and say, see the figure. So let's see, suppose that the alternate interior angles, I'll call them just angle 1, because I don't have many points here to work with, and angle 2 are congruent. So instead of writing down exactly what these are, I'll say see the figure. So I want to call this one angle 1, this one angle 2. Alright, so it would have been hard to talk about these angles otherwise. I would have had to say, you know, let's put a point somewhere out here on this side of this line and a point somewhere out here on this side of this line, and I have to describe exactly what side I mean. And then I could refer to angle Q, P, whatever this point is. But it's a lot easier just to say, here, see the figure. Those are the angles I'm looking at. So anyway, we'll proceed by contradiction. Suppose L and M are not parallel, right? We want to say, the hypotheses are if these two alternate interior angles are congruent, then these two lines must be parallel. So suppose they're not. So we proceed by contradiction. Suppose L and M are not parallel. Well, the good news is if they're not parallel, that means they intersect. And the neutral geometry is an incidence geometry, so two lines can intersect at most 1 point. So they don't sort of zigzag across each other a bunch of times. So because neutral geometry is an incidence geometry, neutral geometry is an incidence geometry, L and M must intersect in exactly 1 point R. So maybe they extend on and they eventually meet at a point R. Now this would be a really common trick in a lot of proofs that you write. So there's an immediate contradiction here. What if I constructed, if they meet in one point R, I have a triangle here, right? This is a triangle. And angle 2 is an exterior angle of this triangle, which means it's bigger than the opposite interior angles. So that means angle 2 is bigger than angle 1. And that contradicts our assumption, our hypotheses, that these two angles are the same in measure. So there's the immediate contradiction. So let's see. Now, angle 2, at least as shown. It could be the other angle is the exterior angle of R is actually on this side, but in my picture I have that angle 2 is the exterior angle. So angle 2 as shown is an exterior angle. Is an exterior angle of triangle PQR. So the measure of angle 2 is bigger than the measure of angle 1. Contradicting that the measure of angle 2 is equal to the measure of angle 1. So not hard to reach the contradiction here, as long as you realize that they can intersect only at one point. So this one point creates a triangle, and then that triangle we've created contradicts the exterior angle theorem immediately. So therefore L and M are parallel. Done. And you've already looked at this for homework, and you've seen that the converse is not true in hyperbolic geometry. So note that we've seen that the converse is not true in hyperbolic geometry. Which would, of course, say if two lines are parallel, then transversals create congruent alternate interior angles. But I wanted to point this out because now we have a model to work with. Think about this model. Here's hyperbolic geometry, the upper half plane model from last time. Here's two parallel lines. Right, now it shouldn't be too hard to construct a transversal of these two lines where it's very clear that the alternate interior angles are not congruent. For example, how about I just do something like, I'll draw a semicircle so that this is, let's see, right around here. So this is a right angle. But then, where's my, let me put it on the interior, here. So, right angle there. But this angle, the alternate interior angle here, that's clearly a lot less than 90, right? So these are two parallel lines that are intersected by a transversal, and yet these alternate interior angles are clearly not congruent. And it's the one nice thing about this model is that the angles you see here, the hyperbolic angles, are the Euclidean angles that you see. Again, distances are not the same at all, but angles are preserved. And to remember which one is not true, which direction is not true, I literally always have to think of a picture like this in my mind. But it's this direction, the converse. So anyway, the alternate interior angle theorem has a whole bunch of immediate corollaries, so we'll state a few. We won't prove them. I might assign the proof of a few of these for homework. But you can restate facts about congruence of alternate interior angles in a few different ways. So corollary. Two lines perpendicular. Two lines perpendicular to the same line are parallel. Really quick sketch of a proof, just draw the situation. Here's two lines that are perpendicular to the same line. What does that mean? That means all of these angles are right angles. What does that mean? That means I have a pair of alternate interior angles. So those two lines must be parallel. So very easy proof, right? It follows immediately from the alternate interior angle theorem. They're not just congruent; they're nice 90-degree angles. Here's another one. Let's see. If two lines are intersected by a transversal such that a pair of corresponding angles formed is congruent, then the two lines are parallel. So it reads a whole lot like the alternate interior angle theorem, and it's implied immediately. The implication should go both ways. I might assign this one for homework, so I don't want to talk about it too much, but it's not hard to see that if you have congruent corresponding angles, then you must have a pair of congruent alternate interior angles. Just use vertical angles there, I think. And we'll do one more corollary, again without proof. Which again should read almost exactly the same, just a different condition on the angles. If two lines are intersected by a transversal such that a pair of interior angles on the same side of the transversal so the pair is supplementary, meaning of course adding to 180 degrees, then the lines are parallel. Again, not a whole lot to do here. This is just sort of take this condition on the pair of interior angles on the same side, think about how the angles relate to each other, and you can show this. This implies that two alternate interior angles must be congruent. So a few immediate corollaries. We might use these in the future instead of a situation where the alternate interior angle theorem is immediately satisfied. Something like this condition on the angles might be instead. So anyway, we've got, what, 25 minutes? What I really want to do today, yes?
So just to be clear, like, if we show that one of these is true, we can go to
Then-
the alternate
then you
interior
can-
angle. And
Then you can just say, if you're in a condition where this is satisfied, now you can say, well, then they're parallel,
Okay.
right?
Yep, cool. That's nice.
Yeah, indeed, I agree. So anyway, yeah, what I really want to do is prove that Euclid's fifth postulate and Playfair's postulate are the same. And I remember grading a few homeworks, and some people said, yeah, they must be sort of the same because they're both statements about parallels, but you know, that doesn't really justify anything. I could make two statements about anything, cats, that are not equivalent to each other. But yeah, so we should prove this. We should prove that they're actually equivalent. So let's see. Euclid's fifth postulate is not an axiom in neutral geometry. And what we're going to do, we present a few statements that are equivalent to it. So we're not going to stop with just Playfair's. We've got a few others that I want to list with proof, but we present a few statements that are equivalent to it. So the first one is one, let's recall Playfair's postulate. Which says if I have a line and a point not on the line, then there's a unique line through P that's parallel to the original line. For every line L and every point P not on L, there exists a unique line there exists a unique line, do I want to give it a name, M, that contains P and is parallel to L. Now, I kind of like calling this Playfair's postulate. It distinguishes it from Euclid's fifth postulate with a very distinguished name. The textbook, however, on the other hand, they start calling this the Euclidean parallel postulate, which is fine because, you know, with the hyperbolic parallel postulates, it's the same situation, but more than one line through P that's parallel. The sort of elliptic case has no lines. So they immediately, they don't call this Playfair's postulate anymore. They call this the Euclidean parallel postulate. And it's important that when you're reading through the text or whatever, and I guess I'll do this now, I'll stick to what the text does because it'll make it read better with homework problems and whatnot. But it's important that you recognize that when I say this word, when I say the Euclidean parallel postulate, I'm not talking about Euclid's fifth postulate anymore, right? If I'm talking about Euclid's fifth postulate, I will say Euclid's fifth postulate. When I say the Euclidean parallel postulate, I mean this, so Playfair's. All right. So our first theorem is going to be that this is equivalent to Euclid's fifth postulate. Something we've said many times already, but finally with proof. Theorem. Euclid's fifth postulate. Oops. Euclid's fifth postulate is equivalent to the Euclidean parallel postulate. So once again here, I mean Playfair's axiom, or postulate. And it took people, Playfair proved this, what, I think in the mid-1700s or something. It took people a long time to realize that these are equivalent, or formally prove that they're equivalent, because it's not necessarily the easiest proof, right? I want to show somehow that if I have two lines cutting through a transversal, where the interior angles on one side are less than 180, and that means that they intersect, well, then that must imply that Playfair's axiom is true. And vice versa. There's two things to do here. We might only do the first direction today. We'll see how this goes. But, yeah, so let's see. Let's let M be a line. Let M be a line. And let A be a point not on M. So I'll construct my picture over here. Here's M. I've got this line M. I've got a point A, not on M. And what do I want to do? So I'm assuming Euclid's fifth postulate is true. So we're going to use Euclid's fifth postulate at some point in this proof. I want to show that there's a unique line through A that's parallel to M. First thing I'm going to do is fairly easy. I'm going to build a line through A that's parallel to M, and then I have to show that that's the only one. All right? So, not too hard. Let's write down the details before I draw it. So, let T be a line through M, or through A rather, through A that is perpendicular to M and intersects M at point B. And let L be a line through A that is perpendicular to T. All right, so what am I doing? I'm coming into A and I'm saying, okay, let's build this line through A that's perpendicular to M. Let's call that line T. This actually takes a little bit of thought. How do I know I can do that, right? In Euclidean geometry, this is no problem. Of course I can. But we're not in Euclidean geometry. How do I know I can just build a line that's perpendicular to M that passes through a particular point? There's a couple of ways you can justify this to yourself. You could just find 2 points on M that are equidistant from A, and then you can construct this perpendicular bisector. Or you could invoke the SMSG angle construction axiom, I think it's number 12, it says that I can construct any angle that I want from a line. So you could think of just construct a whole bunch of perpendiculars until you find the one that actually goes through A. So the justification there isn't actually all that easy, but it's a lot easier to build this one now. By the way, this cuts through at what did I say, point B?
Yeah.
Point B. This one's easier. This is the angle construction axiom that says, okay, from this point A, let's construct a 90 degree. So here I have this other line, L, that's perpendicular to T. This is something we will do many, many, many times in this class. You'll do this construction for homework all the time. It's one of the first steps in many proofs, just these few lines right here. Because what have I done? Well, since both of these are right angles, or how about I go immediately to the alternate interior angle theorem. Since those are right angles, these are perpendicular lines. Or sorry, they're parallel lines. M and L are parallel. So we now have a construction. We had M, we had a point not on M. We now have a parallel through that point. So let's see. By the alternate interior angle theorem, L and M are parallel. We want to show that this is unique. Okay, so finally, we want to show that L is the only line through A that is parallel to M. Let's invoke some colors. Colors are good. So again, I'm pretty sure what I'm going to do here is also something we'll do several times in proofs through this class. So what am I going to do? I'm going to just build some other line. I'm not even going to build it. I'm just going to say I have other lines through A, right? It's an incidence geometry. Let's just take any other line through A and show it can't be parallel to M. So, and let's call this line N. All right, so let N be any other line through A. Now I want to claim that one of the angles between N and T have to be acute. The only way I wouldn't have an acute angle formed between N and T is if all the angles are 90 degrees, right? Otherwise, one of them has to be acute. And they can't all be 90 degrees because N is not the same line as L. So, one of the angles formed by N and T is acute. Because N is not the same line as L. And we'll just give it a name. We'll call it angle N. So in this picture, I've got two of them. We'll invoke this one right here. This angle. There's my angle N. Okay. then angle N plus angle ABC, this angle I haven't defined yet. I actually need to measure. Let me not be lazy with my notation. Measure of angle N plus measure of angle ABC. What is ABC? So C is going to be some point on line M that's on the same side as this acute angle. Again, writing down the details would be annoying stuff about this is on the same side as this thing. So I will once again just say, see the figure. What's true about the sum of these angles in relation to 180 degrees?
It's less than.
Less than, right? This is 90, this is less than 90, so in sum they're less than 180 degrees. Is less than 180 degrees. What does that mean? What was our, we're trying to show that if Euclid's fifth postulate is true, then Playfair's postulate is true, right? Well, that means I can assume that Euclid's fifth postulate, and because these two interior angles on the same side are less than 180 degrees, Euclid's fifth postulate tells me they must intersect, right? So M and N must intersect by Euclid's fifth postulate. And I'm pretty much out of space, but therefore, there is only one line, which we've actually found what it is, it's L, one line through A, parallel to F. That is so it's kind of interesting, and notice, I mean, all these constructions we did, everything we've done so far is true in strictly neutral geometry. It's not until the very end of this proof with all these constructions we finally invoke. Here's Euclid's fifth postulate. If Euclid's fifth postulate is true, then these two lines N and M must actually intersect. Therefore, we have Playfair's because we've shown that L is parallel and N is just any other line, and we've shown that any other line cannot be parallel.
Gotcha.
Awesome. The backwards direction is actually a little bit longer than this. We're in an awkward situation here for time. I think if we tried to start it now, we'd stop in the middle. I don't like stopping proofs in the middle, so we'll end early today. And I'll see you guys on Wednesday.
Okay.